All right, so we'll be doing a brand new chapter today, which is electromagnetic induction. Electromagnetic inductions, well, somehow it's you can say it's a similar to a chapter 4 magnetic field. Okay, but the difference is in chapter 4. Okay, in chapter 4 we use currents to generate motion. In this chapter, we are going to do it in a reverse way. Okay, we use motions to generate induced current. All right, so that is a different thing. So in chapter 4, okay, you use current, you switch on the power supply through the coil, then the coil will start to rotate, right? That is from current generate motion. In this chapter, when it comes to electromagnetic induction, well, you are the one that move the coil, and when you move the coil, induced current will be generated. Okay, so that process terbalik, reverse process. Okay, so chapter 5.1 magnetic flux. Define and use magnetic flux. Now, if you look at the terms, isn't it looks very familiar, magnetic flux? Because in chapter 4, we call B as magnetic flux density. Okay, so first thing, the first terms that we learn in chapter 4 is what we call magnetic flux density. When you add a word magnetic flux density, when you add a word density right here, then this one, it means B. Okay, it means B. But if you're looking at just a magnetic flux, okay, just magnetic flux, then it refers to the symbol phi. All right, so there are two different things. Okay, there are two different things. Don't get confused, don't get mixed up. This is a very common sense mistake in the exam, where students, they tend to mix up these two things. So magnetic flux density dan magnetic flux dia adalah benda yang tidak sama. Okay, dia adalah benda yang tidak sama. Then what exactly is magnetic flux? Okay, before that, let's look at the second learning outcome. Second learning outcome, you have another type of magnetic flux, but now it's called as magnetic flux linkage. So magnetic flux linkage, it's also phi, but this is capital letter phi. Okay, so magnetic flux linkage. So you have three different magnetic flux in this chapter. Okay, you have three different magnetic flux in this chapter: density, and then magnetic flux itself, and magnetic flux linkage. So magnetic flux linkage, what does it mean? By looking at the equations itself, you should know that it is for a case where you have more than one term, because you have a capital letter N in the symbol. Okay, so magnetic flux density refers to magnetic field strength. Magnetic flux is phi. Magnetic flux linkage is the total phi for more than one turn. Okay, total magnetic flux for more than one turn. So three different flux. Okay, three different magnetic flux. They all mean three different things. Okay, so jangan keliru. This is the most important thing in chapter 5. Okay, for me, I think this is the most important thing. If you got confused, if you get mixed up, then you won't be able to do the calculations. So what exactly is magnetic flux? Magnetic flux is defined as a scalar product between the magnetic flux density, between the magnetic flux density with the vector of the area. It is a scalar product. Okay, so mathematically, we can write it as phi 5 equals to B dot A equals to BA. Now, dot product means it is a cos theta, cos function. Okay, it is a cos function, so cos theta. So B dot A and then equals to BA cos theta. And once again, what is a theta? So theta is the angle between vector A and B. Okay, vector A and vector B. So still remember, what does it mean by vector A? So vector A, okay, vector A is the vector that is perpendicular to the plane. Okay, perpendicular to the plane. So if you have a coil, okay, for instance, if you have a coil, so this is the cross-sectional area. So this is the area. Vector A is the vector that is perpendicular to it. Okay, so this is your vector A. Okay, perpendicular to the surface area. So remember, when it comes to calculations, we use area in our calculations, but when it comes to determining the direction, we look at vector A. Okay, vector A and B, that is the angles in our equations. All right, so angles between vector A and vector B. Remember, this is very important. And one more thing, if you look at these equations, okay, you have a part known as cos theta. So remember the things that I told you in chapter 4, whenever you have an equation with cos or sine function, questions like to play with maximum and minimum value. So if you have a cos theta, okay, it is maximum when you have cos 0 degree because it is equals to 1. So this is what we call maximum value. And then it is minimum when you have cos 90 degree because it is 0. And this is what we call minimum value when it comes to a magnetic flux equation. Okay, when it comes to magnetic flux equation. So it is very important to understand these equations, okay, every single part in your equation. So physics dia tak susah. Yang susah sebab apa? Sebab anda tidak kenal anda punya equation. Okay, apa yang pelajar suka buat? Main hafal sahaja. If you memorize without understanding the meanings of every single variable, then it is meaningless. Okay, it is meaningless. So magnetic flux is a scalar quantity and the unit is Weber or Tesla meter square. Now, most of the times we use Weber, okay, WB. So consider a uniform magnetic field passing through a surface area of a single turned coil as shown in the figure below. So first one, if you look at vector A and B, okay, vector A and B, then we have VA cos 0 degree, which is BA. So this one is a maximum value because your cos 0 give you 1. If you look at the second diagram right here, so this is your area. Okay, this is the area for the first diagram, and then this is the area for the second diagram. So vector A perpendicular to it. So vector A and B, they are perpendicular to each other. Therefore, now your flux is 0. So this is the minimum value. Okay, this is the minimum value. So note that the direction of vector A is always perpendicular to the surface area. So this is what I told you before. And the magnetic flux is proportional to the numbers of lines passing through the area. So what does it mean? So how do we know whether an object has a large magnetic flux, a coil experiences a large magnetic flux or a small magnetic flux? You look at the numbers of line passes through the surface area, the cross-sectional area. Okay, so for instance, now if you have two coil, okay, if you have two coil, so same surface area, okay, these two coil, they have same A, right, same A. So now what I'm going to do, I'm going to look at the numbers of line passes through it. So for example, if in a diagram 1, okay, in this first coil, it has a, like, let's say 3 magnetic field line passes through it. And then for this coil number 2, now it has a 5 line passes through it. So obviously number 2, it has a greater magnetic flux because it has more line, okay, more field line passing through the same cross-sectional area. All right, same more magnetic field line passes through the area. Okay, so that is the things that you have to understand, you have to know. Okay, so what is magnetic flux? Magnetic flux, it tells you how many lines passing through the cross-sectional area. More line means greater magnetic flux. Okay, and remember, we have 3 types of flux: flux density, flux linkage. All 3, they refers to different things. B5 and capital letter 5. Okay, and then we have a maximum and minimum value, which depends on the angle. It is maximum when your vector A and B, they are 0 degree. Minimum if they are 90 degree. All right. So this is the introduction part. I give you 2 minutes to write down the important things. Okay, the things that you think you are not understanding. Okay, the things that is not in your books, you can write it down. 2 minutes for you to write it down before I proceed to the next part. Okay, before I proceed to the next part. Okay. So next one, okay, next one is just the equations, magnetic flux linkage. So for a coil of n turns, okay, so just now the equation is for one turn. Now, if you have more than one turns, okay, each turn will have the same magnetic flux passes through it. Therefore, the equations, okay, capital letter phi, okay, capital letter phi equals to n phi equals to NBA cos theta. Okay, so basically you just times the flux with n, and it has a new name called magnetic flux linkage. Okay, so you need to be careful though, because sometimes questions it like to trick the student. Okay, kadang-kadang soalan dia memang suka tipu pelajar. Why? Because it gives you both things. It gives you the numbers of turns, and then it gives you the magnetic flux linkage. Aha. Then if you don't know, when you calculate the total magnetic flux, you still times with the n, then you are going to get it wrong. Okay, sebab apa? If you use n times flux linkage, okay, n times flux linkage, what is going to happen? It's going to become n square phi. So this is wrong. This is not total magnetic flux anymore, okay? This is n times total magnetic flux. Right? So you have to do the questions carefully. Make sure you are looking, make sure you know whether you are looking at magnetic flux linkage, or magnetic flux density. Okay, sebab soalan di chapter ini dia memang suka tipu pelajar. Dia bagi kamu capital letter N, numbers of turns, tapi dia bagi nilai magnetic flux linkage. Dan dia minta Anda kira total magnetic flux. Okay, kira pun, okay, sebab N5 sudah menjadi total. Okay, N5 sudah total. So, kalau kamu darab lagi dengan N, bermaksud kamu akan dapat salah dah. Okay, sebab dia akan jadi N square phi. Dia akan jadi N square phi. Okay, so 5.2 induced EMF. So just now we were looking at magnetic flux. Okay, why is it important? Because magnetic flux will tell us whether there is an induced EMF or not. Okay, so in 5.2, explain induced EMF by using Faraday's experiment. So in this subtopic, we're going to go through 3 experiments today. Okay, we're going to look at 3 experiments today, and then state and use Faraday's law, and state and use Lenz's law to determine direction. So basically, if you look at these two statements, these two learning outcomes, for instance, you should know that 5.2b is for use to calculate the magnitude of EMF. Okay, and then 5.2c is for you to determine direction. Okay, so these two things, basically they come in one set. You use it to calculate the magnitude, and also you use it to determine the direction. Okay, so two of them, they are both for the same thing, for induced EMF and induced current. Okay, the difference is Faraday's is for magnitude, Lenz is for direction. So Faraday's law states that the magnitude of induced EMF is proportional to the rate change of magnetic flux. So rate change of magnetic flux. So EMF is proportional, okay, proportional to rate change. What does it mean by rate change? So rate change means it is d phi over dt. Okay, d phi over dt, but it comes with a negative sign right here. Why? Because this negative sign, it tells you the directions of induced EMF, it always opposes the change of magnetic flux producing it. Okay, so when you combine these two laws together, it gives you one equation. Okay, it gives you one equation, which is EMF is proportional to negative d phi over dt. Faraday's give you this one, and Lenz give you the direction. Okay, Lenz give you the direction. So combine two things, you obtain these equations. Right. So rate change in magnetic flux. That's why you need to understand what is magnetic flux first. Okay, so by changing the magnetic flux, then you will be able to generate induced EMF. Okay, induced EMF will be generated. So for coil of n turns, okay, for a coil of n turns, EMF is then equals to negative n d phi over dt. Okay, and d phi is a change, therefore negative n, and then final minus initial over the times given. Okay, over a period of time, dt. So phi final minus phi initial, right? Phi final minus phi initial. So basically, okay, basically, if you look at the equation just now, we have a flux equals to NBA, NBA, wait, yeah, it's not NBA, it's BA. Flux equals to BA cos theta. So meaning that by changing either one terms, okay, by changing either the strength of the magnetic field, the cross-sectional area of the coil, or the angles, then you will be able to change the magnetic flux. If magnetic flux changes, then it leads to the generations of induced EMF. Okay, change it. Okay, change B, change angle, change either one of them, change the cross-sectional area, then it generate. Okay, it generate induced EMF. Okay, induced EMF. Now, to be more precise, actually, I encourage you guys. Okay, wait, yeah, let me erase it first. Actually, I encourage you guys to write it as EMF and then IND right here to show that this is induced EMF. Why? Because in equations, okay, in equations, you will have a normal EMF that is coming from the power supply. You will have an induced EMF that is being generated in a coil. And then you will have a normal current that is coming from the power supply. And also, you will have an induced current that is being generated in a coil due to the change in magnetic flux, right? So whenever we talk about induced EMF, actually I encourage my students to put subscript IND, okay, subscript IND, to show that this set is for induced, okay, it's for induced situation, induced EMF and current, okay, which is generated because of the change in magnetic flux. And then this set, okay, this set of information, it is coming from your power supply. Okay, this is coming from your power supply. So kamu ada dua set punya maklumat, dua set punya EMF dan I. Okay, EMF and I. So you have to know which one is coming from which part, which component. All right, so when you read the questions, make sure you know, okay, make sure you know how to distinguish which one belongs to induced information, induced set, which one belongs to the normal set, the power supply set. Okay, so note that, okay, here bullet point E is important. Okay, kalau kamu tengok E, when a magnetic flux increase, okay, the change in magnetic flux is positive. So flux increase, d phi is positive. Thus, induced EMF is negative. This one you need to know, because sometimes questions won't tell you whether it is positive or negative. You yourself need to know whether the induced EMF given is positive value or a negative value. How do you know? You look at the change in the flux. If a change in the flux is positive, then induced EMF is negative. If change in the flux is negative, then induced EMF is positive. Why? Because negative and the negative sign in the equation, it gives you a positive induced EMF. So what does it mean by negative induced EMF? It means it is being generated to oppose the increasing in magnetic flux. Because when you change, kalau kamu ubah nilai B, nilai A, or cos theta, if you change it, you will either increase the flux or decrease the flux. If flux increase, okay, then induced EMF will be generated to oppose. So the keywords in this chapter is actually oppose. Anything this induced EMF does is try to oppose what you have done to the coil. Okay, if you make the magnetic flux increase, then induced EMF will try to oppose the increment. Okay, it will try to oppose. It doesn't want to increase. But if you decrease, okay, if a magnetic flux is decreased, okay, then d phi is negative. Therefore, induced EMF is positive. Why? Because it is to oppose the decreasing in magnetic flux. So now it doesn't want to decrease. Therefore, you have a positive value to top up the value that you took away from the system. Okay, so the idea is like this. If you have a positive d phi, kalau kamu ada positive d phi, Okay, it means that you cause your action causes the flux to increase, to become stronger. So what happens right here? Induced EMF is negative. Why? Because it tries to remove the effects that you add to the coil. Okay, efek yang tindakan kamu, okay, yang bagi kepada coil yang sedia ada. Contohnya, okay, you cause the flux to increase. This induced EMF try to negate the effect. It try to take away the increment from you. Okay, that's why you have a negative value. But if your action causes the magnetic flux to decrease, meaning that now your device is a negative value. So what happens in the coil? This induced EMF will be generated to top up the value that you took away from the system. Okay, dia akan top up balik. That's why dia adalah positif. Okay, tadi negatif sebab dia nak kurangkan benda yang kamu tambah ke dalam sistem. Tetapi kalau sekarang dia ada negatif, okay, so induced EMF akan jadi positif because it tries to top up. Okay, it tries to top up the magnetic flux that you took away from the system. All right. So you have to understand though. Make sure you understand, because if you are not understanding these two statement, kalau kamu tak faham dua statement ini, maka nanti bila kita terangkan eksperimen, okay, when we go through the 3 experiment, you'll be blur. Okay, kamu akan blur. Kamu akan langsung tak faham apa yang saya cakap nanti. Alright, so you need to understand these 2 statements first. This 2 statement is very important. Okay, this 2 statement is very important. Okay, now let's look at it in terms of a diagram. Right, so first thing, what does it mean by Lenz's law? So Lenz's law, okay, it states that an induced electric current always flows in the directions to oppose the change producing it. Okay, so oppose, that is the keywords in explaining the direction. Okay, in explaining Lenz's law. So this law is essentially a form of the law of conservation of energy. Okay, so energy is conserved. Why conserve? When you add the energy into the system, induced EMF try to take away the additional energy. Okay, so the total becomes 0. But if you take away the energy from it, induced EMF will try to top up the energy that you took away. Once again, it is conserved. Okay, so it is essentially a form of the law of conservation of energy. So the directions of induced current can be determined by using right-hand grip rule. Okay, you can use it by right-hand grip rule. Idea exactly same as how you determine directions of magnetic field, directions of a current in magnetic field in chapter 4. Okay, where your thumbs represent current, fingers represent magnetic field. The only difference is in this chapter, thumb is still representing current, but it represents the directions of induced current. These 4 fingers is still representing the directions of magnetic field, but now it represents the directions of induced magnetic field. Okay, induced current and induced magnetic field. Okay, induced current and induced magnetic field. So exactly the same. Okay, tangan yang sama. Tetapi apa? Tetapi dia sekarang gunakan untuk induce punya maklumat. So if you use your right-hand rule for normal current, then the field that you use must be coming from the normal magnetic field. If you use it for induced current, then the 4 fingers must be coming from induced magnetic field. Dia adalah 2 keluarga berlainan. Okay, induced set is for induced set. Okay, induced information is for induced family. And then normal information is for normal family. Okay, tak boleh silang. Even if you are going to calculate the VIR, for example, contoh lah, kalau kamu nak kira V equals to IR, okay, then if you are using V induced, then I must be induced. Dia tak boleh V biasa, I induced. No, cannot. Okay, so must be from the same family. Okay, must be coming from the same family. So for example, B, okay, kalau kita kira B equals to IL cross V kan? Ya rasanya. F equals to IL cross V. Saya ada equation for conductor. V equals to mu naught. Mu naught ba ya? Saya tak hafal equation. Saya kena cari saya. Mu naught and then okay. So mu naught I over 2 pi r. Okay, so if you're calculating some normal magnetic field, then B is from the normal, I is for the normal current. If you calculate B induced, then you must use the I induced over 2 pi r. Okay, so that is the idea. That is the idea. So they must be coming from the same family. Okay, induced punya family untuk induced punya maklumat. Biasa punya untuk biasa punya maklumat. Alright, so don't get confused, don't get mixed up. And this is one of the reasons why I tell you it's very important to know the equations in chapter 2, because even if you look at the equations of magnetic flux, it comes with a B right here. Okay, kamu ada symbol B di sini. So you still need to know how to calculate B from chapter 4. Okay, from chapter 4. All right, so the directions of induced current first can be determined by using right-hand grip rule, or you can use it by, you can use a Fleming. Okay, you can use a Fleming's right-hand rule. Okay, Fleming's right-hand rules to determine the directions of induced EMF. Okay, induced current or induced EMF, they are both pointing toward the same direction. Okay, so induced EMF or current. Okay, induced current. So where your thumb representing the directions of motion, field is the fingers, the first fingers, and then your second finger, your middle fingers, is representing the directions of induced EMF or induced current. Okay, induced EMF or induced current. So both hands can be used. Okay, both hands, kedua-dua adalah betul. It's up to you which one you want to use. Okay, I'm showing you both. In your books, you are given the right-hand grip rule. Okay, you are given the right-hand grip rule. But if you look at reference books, some of the reference book, they use Fleming's right-hand rules. Both are correct. Okay, just that they use a different idea in determining the value. Okay, in determining the values of, in determining the directions of induced current. Again, not value, sorry, but the directions of induced current. Okay, now what is an induced magnetic field? If you want to use right-hand grip rule, then you need to understand what does it mean by induced magnetic field. Right? Kalau nak guna right-hand grip rule, first thing apa yang kita kena tahu? Kita kena tahu arah induced magnetic field. So this diagram is not in your books. Okay, if you want to write it down, you may write it down. So the induced magnetic field in the loop wire will oppose the change in magnetic flux through the loop. If you try to increase the flux through the loop, okay, so for example, if you look at this diagram, now if you move this piece of magnet towards the coil, you are trying to increase the coil, the numbers of line passes through the coil. Okay, so initially, maybe if you put a magnet right here, okay, if you put a magnet right here, initially maybe just 2 lines passes through it, 3 lines passes through it. Okay, so the other 2, they are not passes through it. When you move this magnet towards the coil, more and more line will be able to pass through the coil. Okay, lagi banyak line akan melalui coil yang sama. So that means you try to increase your action, try to increase the flux through the loop. Therefore, induced magnetic field will be generated to oppose the increase. Therefore, it's in the opposite direction. Because now you try to add more line to the coil. Okay, you try to add the numbers of line passes through the coil. Okay, increase the numbers of line passes through the coil. So what is going to happen? Induced B will be generated in the opposite directions to cancel out the numbers of line that you try to add to the coil. Okay, kalau kamu nak tambah 2 line, mungkin dia akan cuba untuk cancel out that 2 line. So B will be generated in the opposite direction. So by using this B induced, you then will be able to determine the directions of induced current by using your right-hand grip rule. Okay, ini untuk right-hand grip rule punya. Okay, this is for right-hand grip rule. Okay, this is for right-hand grip rule. Kalau kamu guna Fleming's hand, then you are just looking at the normal field. Okay, you are not looking at induced magnetic field, but this is normal electric field. Okay, this is normal magnetic field. Now this one, the one that I'm explaining, is for induced magnetic field. It's for right-hand grip rule. Okay, and frankly speaking, I like to use right-hand grip rule more than Fleming's hand rule. Sebab apa? Sebab right-hand grip rule can be used in all sort of situation. Whereas your Fleming right-hand rule can only be used in a straight conductor. Okay, dia cuma boleh guna untuk straight conductor. Dia tak boleh guna untuk coil. So kalau untuk coil pun, macam mana pun, you have to go back to right-hand grip rule. Okay, that's why buku anda, dia bagi kamu right-hand grip rule. Sebab right-hand grip rule can be used in all sort of experiment, but Fleming sense rule can only be used for a straight conductor. Okay, so now if you look at the second case, okay, if you look at second case, if you try to decrease the flux, what does it mean by you try to decrease the flux? For example, just now I have 3 lines passes through the coil. Now I move this magnet away. When you pull this magnet away, less line, okay, less line will be able to pass through the coil. Okay, less line passes through the coil right now. So just now I have 3 lines. Okay, I have 3 lines. When you pull this magnet away, okay, maybe now you have just 1 line. Okay, maybe now you have just 1 line passes through it. The other 4 lines, they are not passes through the coil anymore. So what happens right here is induced magnetic field will replace the line that you took away from it. So it will be generated in the same direction. Same direction. That's why you have positive value. Okay, that's why you have positive induced EMF, because it's being generated in the same direction to top up the line that you take away from it. So induced magnetic field, it depends on whether your action causes the flux to increase or decrease. If it causes it to increase, then B induced will be generated in the direction that is opposed to the original magnetic field. If you decrease the flux, then B induced will be generated in a direction that is same as the magnetic field. Okay, ini B biasa, ini B biasa, normal B coming from magnet. B induced, it depends on your action. Okay, it depends on whether the flux is increased or decreased. If flux increase, B and B induced, okay, B and B induced, opposite direction. If decreased, then B and B induced, same direction. Okay, same direction. So that's it. Okay, that is the Lenz's law. That is how we use Lenz's law to determine the direction. So induced magnetic field is generated in the direction that is opposed the change. Okay, so oppose the change. Ini kata kunci. This is the keywords that we use in our explanation. So chapter 5, when it comes to explanation type questions, how are you going to explain it? You explain from what is the things that causes the change in magnetic flux, either the A, the B, or the angle. Okay, because of the change of one of the variable just now, it leads to the change in magnetic flux. When there's a change in magnetic flux, induced EMF is being generated. Okay, induced EMF is being generated. And then the directions of the induced EMF is opposed to the change of the magnetic flux through the loop. That is how you answer explanation type questions in chapter 5. All right. Okay, so this part, well, this one actually is the most important thing in chapter 5. Kalau Anda boleh faham Faradays Law, Anda boleh faham Lenz's Law, then after this, the 3 experiment and 2 induction process, it shouldn't be an issue for you. Okay, so I give you 3 minutes to write it down, especially the diagram on the right-hand side. Okay, pastikan Anda faham muka surat ini betul-betul. Kalau ada apa-apa tak faham, Anda tanya sekarang. Okay, sebab kalau Anda tak faham kedua-dua hukum ini, nanti bila saya terang 3 eksperimen dan 2 induction proses, Anda tak akan faham langsung. Okay, Anda tak akan faham langsung. Sebab dia akan guna idea di sini, di muka surat ini. This is the most important thing in chapter 5. Okay, so no question, good. If no questions, then we will look at, okay, the process. Okay, so this is the intro again, and then after that, we'll go through 3 experiments. So once you understand what is the induced magnetic field, we can go through the 3 experiments very quick. Okay, we can finish it very quick. So now let's go through the applications of Faraday's and Lenz's law again. Okay, so we're going to go through what does it mean by change in magnetic flux and so on. So figure shows a conducting loop connected to a sensitive emitter. Okay, so basically you have just a loop with emitter, no power supply, no battery, nothing. Okay, so because there's no battery or other source of EMF included, therefore there is no current in the circuit initially. Okay, there's no current initially. So however, if we move a magnet towards the loop, a current suddenly appears in the circuit. And the current disappears when the magnet stops. If we move the magnet away, a current again suddenly appears. But now the current is flowing in the opposite direction. Okay, that is the observation. That is what Faraday's observed actually. Okay, so Faraday's experiment, he started an experiment with just an emitter and a coil. Okay, and then he used a piece of magnet, he moved the magnet, and suddenly you notice that, oh, this is what happened. If you move it towards the coil, there's a current. But if you move away, there's a current again, but in the opposite direction. But if the magnet is not moving, then, well, emitter, it goes back to 0. So from there, he then found out that, okay, your induced EMF, it depends on the magnetic flux. Okay, that is what Faraday's observed. When there is a change in the magnetic flux, there's an induced EMF. And then let's tell us that the reason why the current is in the opposite direction, that is because the induced current generated is always opposed to the flux that generating it. Okay, the flux in the coil. So explanation. So what happens right here? Initially, you place a magnet that is far away from the loop. Okay, the magnet initially distant. Okay, the magnet initially is distant, is far away from the loop. No field line passes through the coil. Okay, tak ada field line melalui coil ini. No magnetic flux passes through the loop. Okay, because no line passes through the surface area right here, therefore no flux through the loop. Since okay, this is a case 1, I'm going to call it flux 1. So equals to B1 A cos theta. In this case, because it's far away from a loop, okay, therefore we say B1 equals to 0. If B1 equals to 0, then your flux 1 is also equals to 0. So what happens in the second diagram? When you move your magnet towards the coil, okay, what happens right here is now that you have a field line passes through it. Okay, this 3 field line passes through the coil. So when the north pole of the magnet moves towards the loop, the flux through the loop increases the numbers of magnetic field line passes through the loop. Okay, the numbers of magnetic field line passes through the loop increase. So what happens right here? Now I have flux number 2. Okay, I move it towards here. So now this is case number 2, the situation number 2. So B2 A cos theta. Now my B2 is no longer equals to 0. Okay, the numbers of field passes through the coil is no longer equals to 0. So it is equals to B. Okay, B2 is equals to B. So B2 is equals to B. What does it mean? It means now my magnetic flux is equals to BA. Okay, so from Faraday's law, induced EMF is equals to negative d flux over dt, which is equals to flux number 2 minus flux number 1, okay, over t. Okay, flux final minus flux initial. Okay, so wait, my negative sign is missing. All right, negative flux 2 minus flux 1 over t. Therefore, because it is not equals to 0, okay, it is not equals to 0, EMF induced will produce the I induced. Okay, there's a change in flux, therefore induced EMF is being generated, is being produced, and since you have induced EMF, therefore induced current will be generated as well, will be produced. All right, so process dia begini. Okay, you change the B. Okay, B induced changes. Okay, B induced ada. It leads to what? It leads to the change in magnetic flux. Okay, atau kita terbalikkan dia. So because of the change in magnetic flux, B induced is being generated. B induced give you EMF induced. EMF induced then give you I induced. Okay, EMF induced then give you I induced. Okay, next, directions of I induced. Okay, directions of I induced. Based on Lenz's law, okay, just now we use it to determine the magnitude. So when it comes to direction, based on Lenz's law, the I induced must set up its own field. Okay, its own field B induced in a direction that opposes the change in magnetic flux. So just now we increase the B through the coil. Initially B is 0. B1 equals to 0. Situations 1, time 1. When times equals to T2, we have B2 equals to B. So from here to here, okay, from a first diagram to a second diagram, B increase. Okay, when B increase, what happened? B induced, okay, B induced will be generated in the opposite direction. Okay, so the dotted line right here actually is representing B induced. Okay, kamu punya dotted line. Let me highlight it. This one is actually your B induced. Okay, so this is your B induced. So B induced is being generated in the opposite direction because it tried to push the line that you added in the loop. Okay, you added in the loop. You add 3 lines, it generates 3 lines. Try to push it away, try to cancel it out. So by using B induced, you can then determine directions of I induced by using your right hand grip rule. Okay, so you hold the loop, you will see that I induced in these situations in the examples given is flowing in the anti-clockwise direction. Okay, so kamu ada I induced di sini. Okay, kamu ada I induced di sini. So that is case number 1. When you move it towards the loop. Okay, when you move it towards the loop. So now, since your magnet is already very close to the loop, okay, your magnet is already positioned at here, located at here. So what happened? You let it stop. Okay, the keywords right here is here. When you stop the magnet, okay, when you stop the magnet, what happened? As the magnet bar stop, okay, the ammeter shows 0. Why? Because there's no change in the magnetic flux. What does it mean by no change in the magnetic flux? So just now I call this situation 1, I call this situation 2. If I let the process continue, and this will be a step number 3. In the step number 3, let us calculate magnetic flux 3. Okay, so maybe just now is T equals to 1 second, T equals to 2 seconds, this is T equals to 3 seconds. So now you let it stop. When you let it stop, we have B3A cos theta. And in this case, B3 is still equals to B because now you let it stop. Okay, kamu biarkan dia berhenti. You move the magnet from far away and then you let it stop for a second, for example. And what happened in this 1 second? The B is still equals to B. Okay, B3 is still equals to B. The B remain the same. Okay, if the B remain the same, then your flux is still equals to BA. So if it's still equals to BA, what does it mean? Now, if you look at induced EMF, it is equals to d phi over dt. Once again, saya termakan saya punya negatif. Negative. The flux over dt. The flux over dt from situation number 2 to situation number 3 is flux number 3 minus flux number 2 over time. Flux number 2 just now I obtained BA. Flux number 3, I also got BA because it stopped, it's not moving. So BA minus BA over T, which give you 0. So in this case, your magnetic flux is 0. Okay, your induced induced EMF is 0. Okay, induced EMF is 0. because there's no change in the magnetic flux. Because when it stops, the numbers of field line passes through it. Okay, the numbers of the field line passes through it is still the same. It remains the same. Okay, if it remains the same, then no change in magnetic flux. No change in magnetic flux means no induced EMF. No induced EMF means no induced current. No induced currents, what does it mean? It means ammeter will show zero deflection. Aha, nampak tak? Okay, so what happens from case number 2 to 3? Okay, from situation 2 to situation 3, B constant. Okay, B constant leads to d phi equals to 0. D phi equals to 0 give you induced EMF equals to 0. Induced EMF equals to 0 means that no induced current. No induced currents means no deflection. No deflection. So that is how you explain it when it comes to explanation type question. Okay, when it comes to explanation type questions. Then now let us continue the process. Just now I stopped for a moment. What happened now? I'm going to pull it out. Okay, I'm going to pull it out. So when the north pole of the magnet moved away from the loop from this process number 3, the flux through the loop decreased. Why? Because now the numbers of line passes through it decreased. Now no more line passes through the coil. Okay, no more line passes through the coil. So flux 4 equals to B4A cos theta, which in this case, because no field line passes through the loop, B4 equals to 0. So flux 4 also equals to 0. So from Faraday's law, EMF induced is equals to negative d phi over dt, which is then equals to, okay, negative flux 4 minus flux 3 over dt. Okay, over time. Okay, oops, over the time. So D4 is a 0, D3 is BA. Therefore, it is a non-zero value. If it is not a zero value, then it will produce induced current. Okay, it will produce induced current. So how to determine the directions of induced current? Now, because you decrease the numbers of line, okay, so from process 3 to process number 4, B decreased. If B decreased, then B induced is in the same direction. Okay, it tries to top up. So now you have B induced in the same direction. So when you have B induced in the same direction, by using your right hand grip rule again, then you will be able to determine the directions of I induced, which is now in the clockwise direction. Okay, which is now moving in the clockwise direction. So that is the whole process from not moving, and then you move it towards the coil, and then you stop again, and then you move it away from the coil. So ada 4 step di sini, okay, 4 step. So what happened in this 4 step? That is what happened right here. Okay, that is what happened right here. So the first one, because B changes, so B changes lead to, okay, change in magnetic flux. Change in magnetic flux generate B induced. B induced give you EMF induced, which will give you I induced. And then the second case, B constant. B constant means no change in magnetic flux. No change in magnetic flux, no induced, no deflection. Okay, and then from a 3 to 4, once again, B changes. B changes lead to, okay, change in magnetic flux. Change in magnetic flux give you induced EMF, which then give you I induced. Okay, I induced means that now there's a deflection in the ammeter again. Okay, just that now the direction is opposite direction. Okay, just now anti-clockwise, now clockwise direction. All right. So yeah, that is the applications of Faraday's and Lenz's law. Okay, Faraday's and Lenz's law. Okay, so well, again, I give you 2 minutes to go through it. Okay, then we're going to go through the process quickly. Okay, kita akan go through the process. Cepat saja. Okay, 2 minutes for you to digest the things that we learned right here. Now we're going to go through the process quickly, maybe in another 10 minutes. Okay, so kita akan habis lewat sedikit sahaja. Okay, so now you have experiment 1. Just now we were looking at coil. Now we are looking at this solenoid. Okay, you just replace the coil with the solenoid. So basically, it's very same. Okay, the idea is very similar. Just that now you just change the object right here. Okay, you just change the object right here. So the magnitude of the magnetic field of the solenoid increase when you move towards a solenoid. All right, when you move this B towards a solenoid, more magnetic field line passes through it. So increase in magnetic field line causes a change in flux. And then there's a change in the flux, then EMF will be generated and it will produce IEMF. Okay, it will produce IEMF. Okay, so this is a mistake. Actually, it should be flux is proportional to B. Okay, flux is proportional to B. So according to Lenz's law, induced current will flow in a direction that will produce a B induced opposed to the change in the flux. Now, why is it important to know this statement? You need to know the directions of B induced in order to determine the directions of a current flow. Why? Because by using right-hand grip rule, okay, this north pole is the induced north pole. Okay, induced north pole. So if you know when you move the magnet towards it, okay, N pole towards it, here it will generate an N pole to push the magnet away because it doesn't want you to increase the magnetic field line passing through it. So north pole will be generated at here when you move the magnet towards it. So by using your right hand grip rule, okay, you know the directions of the induced north pole. From there, you then determine the directions of induced current. Okay, kamu guna right hand grip rule juga, just that now this right hand grip rule is the right hand grip rule for a solenoid. So now you have the directions of induced magnetic field to oppose the change of flux. By using your right hand grip rule, you'll be able to determine the directions of I induced. Okay, you move it towards the solenoid. Solenoid will try to push the magnet away because it doesn't want the magnet to come closer to it. Okay, it wants the magnet to stay at its original position. It doesn't want any changes. So same pole will be generated. Okay, N pole akan di-generate di sini. But if we pull it away, what is going to happen? As you can see right here, S pole is being generated right here because it doesn't want the magnet to go away right now. Okay, because if you move the magnet away, the magnetic field line passes through the solenoid will decrease, and that is not what it wants. Okay, it wants the magnet to stay. It wants the magnetic field to be kept constant. Okay, so what is going to happen right here? It will generate a south pole. If here is the induced south pole, then induced north pole would be in the opposite direction. Okay, kalau kamu taruh dia keluar, dia tak akan bagi dia keluar. Okay, dia tak nak dia keluar. So kalau dia tak nak dia keluar, apa yang terjadi? Dia akan generate satu south pole di sini. Because it will try to attract the magnet. Okay, it wants the magnet to stay stationary, not moving. So an opposite pole will be generated. So decreasing in magnetic field causes a change in flux. Okay, and once again, ada typo di sini. Okay, is proportional to B. All right, so since the flux changes, EMF is generated and it will produce IEMF. Nampak tak? Dia punya explanation sama. Even though now you change the object from coil to solenoid. Okay, even though now you change the object from coil to solenoid. So according to Lenz's law, okay, you see how they explain the directions by using Lenz's law. It will produce a magnetic field induced magnetic field to oppose the change in flux. Okay, and therefore the directions can be determined by using right-hand grip rule. So here in this diagram, once again, the I in the diagram should be I induced. Okay, should be I induced. So this is induced north pole. Okay, kamu tambah sedikit di dalam kamu punya buku. Ada beberapa ayat yang hilang. Alright, induced north pole, induced current, induced current. Okay, so this is flux proportional to B. Okay, flux proportional to B. So the way you explain it, you see, what is the things that causes the flux to change? Okay, you look at here. Okay, this one is say B changes. Okay, B changes. B changes lead to the flux. The flux changes cause induced EMF. Induced EMF produce induced current. And then direction oppose the change. That's why saya kata, kalau kamu paham bukan surat yang sebelum ini, then all this experiment, okay, you should know how to explain it. You should know what happens in all this experiment. Okay, so this is B changes. Now let's look at the next example. Next example, this is a conductor. Okay, this is a conductor. So when a conductor moves with a constant velocity, now, actually when it comes to this case, when you are given a conductor, what are you going to do? It is up to you whether you want to form a loop on the left hand side or on the right hand side. Okay, in this second experiment, actually you are given a conductor in a magnetic field. But actually this one shouldn't happen, you know, because in this question you need a complete loop. So it is up to you. Okay, dia terpulang pada Anda. Whether you want to form a loop on the right hand side or you want to form a loop on the left hand side. Dia tak kisah. If you are just given a conductor without a complete loop, then you yourself, you have to form a loop. Okay, you can form a loop on the right hand side or you can form a loop on the left hand side. It doesn't matter. Okay, it doesn't matter. So when the conductor moves with a constant velocity, the area swept out by the conductor increases. Okay, so you're looking at what happens in this area. Okay, you're looking at what happens in this area. So let's say if you look at this diagram, according to the diagram, now it tells you you move the conductor to the right hand side. Okay, so you move this conductor to the right hand side. This is your V. Okay, this is your V. Okay, so these two examples, I'm going to show you both. Okay, I'm going to show you both. So if you move the conductor to the right hand side, what happened in the first diagram if you assume the loop is on the right hand side? Kalau kamu assume the loop is on the right hand side, what is going to happen? A decrease. Okay, A decrease. Area jadi kecil. Okay, A decrease. If you move it to the right hand side in the second diagram, then A increase. Okay, A increase. So what happens right here is that if A, or in first diagram A decrease, in the second diagram A increase, both of them, it tells you what? It tells you A changes. When A changes, it leads to the flux. Okay, and the flux, it gives you induced EMF, and thus you have I induced. Just that now, how are you going to determine the direction of the current? How are you going to determine the directions for I induced? So if A decrease, okay, if A decrease, your flux decrease. If flux decrease, what does it mean? Okay, it means B induced will be generated in the same direction. Same direction as B original, magnetic field. So if you look at the first diagram, okay, if you look at the first diagram right here, original magnetic field is into the page. So B induced will be generated into the page as well. Okay, will be generated into the page as well. So by using your right hand grip rule, okay, by using your right hand grip rule, okay, you hold this loop, kamu pegang loop ini, you will see that I induced is being generated in the clockwise direction. Okay, in the clockwise direction. So this is your I induced. Okay, this is your I induced, and this is your I induced. Same as the diagrams given right here. Okay, same as the diagram given right here. Now let's look at the second diagram. In the second diagram, how are we going to determine the direction? So in the second diagram, okay, when I pull the conductor to the right hand side, I'm increasing the area. As the area increase, flux increase. If flux increase, B induced is being generated in the opposite direction. Okay, opposite to B. So I have B into the page, meaning that in this case, my B induced will be out of the page. Okay, yang warna hijau ini, this is my B induced. B induced out of the page. If I use B induced out of the page and I use right hand grip rule, okay, I grip the wire, therefore my I induced is now moving in the anti-clockwise direction. So that's why I told you just now, it doesn't matter whether you want to form the loop on the right hand side or on the left hand side. You're still going to get the I induced in the same direction. Okay, I induced kamu tetap akan menghadap ke arah yang sama. Okay, so both of them, okay, they will give you the same direction. Okay, they will give you the same direction. So if you're given just a conductor, then you need to form a complete loop. Okay, you need to form a complete loop. So increasing the area will cause a change in magnetic flux, blah, blah, blah. So it's proportional. Okay, so based on the Faraday's law, EMF, okay, now all these explanations, they are all the same. Okay, all these explanations, they are all the same. So basically, in your explanation, you don't have to explain whether A increase or A decrease. Okay, you just say A changes. A changes leads to the change in magnetic flux. Okay, and since magnetic flux is proportional to A, okay, and then it's proportional to EMF, therefore induced EMF is generated and thus it produces induced current. Nampak tak? Semua dia sama. Okay, semua dia sama. So change in A causes a change in flux. Okay, change in flux leads to the change in the productions of induced EMF, and induced EMF would then produce induced current. So according to Lenz's law, okay, produce a induced current will flow in a direction that will produce a magnetic field, induced magnetic field, to oppose the change in magnetic flux. Okay, through the increasing of the area swelled by the straight conductor. So in this example given, dalam buku Anda, it's actually assuming the loop is here. Okay, it's assume the loop. Okay, this is a loop. Tapi dalam exam, it's up to you. Okay, whether you want to make the loop on the right-hand side or on the left-hand side. Both are correct. Okay, so I give you 2 minutes to write it down, especially the diagram on the right-hand side. Okay, especially the diagram on the right-hand side. This one, it truly helps you to understand what does it mean by I induced and how, what does it mean by B induced and how to determine the directions of I induced by using right-hand grip rule. Okay, so bagi Anda 2 minit untuk catat 2 diagram di sebelah kanan ini. Okay, di sebelah kanan ini. And then we'll go through the last experiment and then I'll let you guys off. Okay, setakat ini ada apa-apa masalah tak? Ada yang rasa masih pening ke, tak faham ke? Okay, kalau tak faham kena tanya ya, sebab memang chapter ini dia main dengan benda ini saja. The same thing, it keeps repeating over and over again. Right? Dalam semua proses, including the induction process that we're going to go through in the next lesson. Okay. So, right. Second experiment, we are done. Okay, second experiment is for a straight conductor. So just now we have solenoid. Now we have a straight conductor. Now, of course, sometimes students, they think it's quite hard to understand this one. They want to use a left-hand rule. Okay, Fleming left-hand rule. Also can, nothing's wrong. Cuma itulah yang saya beritahu kamu tadi. Fleming left-hand rule, it can only be used in this example. Okay, kalau kamu nak guna untuk solenoid ke, nak guna untuk case seterusnya, tak boleh. Okay, tak boleh. Fleming's right-hand rule can only be used for the second experiment. All right. So now experiment number 3. Experiment number 3, when the coil is being made rotate, now you have a rotating coil. So experiment 1, we have a solenoid. Okay, we have a solenoid. Experiment 2, we have straight conductor. Okay, straight conductor. Experiment number 3, we have rotating coil. What does it mean by rotating coil? If you have a rotating coil, as it rotates, it will change the angle. So magnetic flux changes due to the change in the angle, okay, in angle between vector A and vector B. So because flux is proportional to cos theta, based on Faraday's law, when there's a change in the magnetic flux, induced EMF will be generated, and thus it will produce induced current. Okay, it will produce induced current. So as a coil rotates with a constant angular velocity in a uniform magnetic field, it produces a sinusoidal alternating EMF as shown in the figure. Because the induced EMF, it keeps increasing, decrease, go to zero, increase, decrease, go to zero, and so on. Okay, so when you have a rotating coil, what happens right here is there is a change in the flux. Okay, so you look at whether it's changed in the angle. Okay, if it's changing from 0 degree to 90 degree, means that flux increase. Okay, from 0 degree to 90 degree means flux increase. Okay, kita punya phi increase. So once you know whether your flux increase or decrease, you can then proceed to determining the directions of induced magnetic field. Sama juga, even rotating coil, you can use your right hand grip rule to determine the directions of current. So after it passes through the maximum angle, the 90 degree, from 90 as it goes back to 0 degree, your flux decrease. All right, your flux decrease. So this is what happened. Okay, this is what happens in a coil. So dia akan asyik berubah. Your EMF will keep changing because of the angle. Okay, because of the angles. All right, so this one, experiment number 3, basically it just wanted you to know when there's a change in the angles between vector A and magnetic field. Okay, remember, you are looking at vector A. Okay, you are looking at the vector A. So, yes, okay, now, yeah. So now we are done with all 3 experiments. Okay, so this is just a derivation. Now, derivations, I will leave it to you. Okay, kamu sendiri go through derivations there. Because if I explain derivations once again, okay, it would just, yeah, I think it's quite boring if I just derive it again, since it's given in your books already. So what I'm not going to give you, I'm just going to give you the final equation. Okay, saya bagi kamu equations terakhir. Derivations, anda sendiri tengok. Okay, I told you the experiment already. I told you what happens already. So the equations, okay, you just write it down. Here is a induced EMF is equals to, okay, B L V sine theta. Okay, sine theta. And then here for a rectangular coil of n turns, basically you just plus n in front of it. N BLV sine theta. Okay. So this is for a straight conductor. Okay, straight conductor, as you pull it, you are changing the area. So from changing the area, you then derive and obtain this equation. Okay, and then obtain this equation. Now for the second case, okay, for our second case, experiment, we have 3 experiments just now. Now when it comes to here, okay, you have 3 examples right here. Okay, 3 examples where you can use in a calculation. Straight conductor, coil, and rotating coil. Now what can we do to a coil? We can either change the B and A is kept constant, or you change the A and B is kept constant. Okay, because like I told you before, we have magnetic flux equals to BA cos theta. So basically we are going to see, okay, what is the variable that we can change right here. Okay, we are changing right here. So when it comes to a coil, you can either change the magnetic field strength or you change the surface area. If you change B, then the equation is simply EMF equals to negative NA but dB over dt, because now you're changing the B. If you change A, then it is EMF equals to negative B dA over dt. Okay, dA over dt. So you change B or change A. If you change the angle, then you have a rotating coil. So rotating coil, if you derive the equations, eventually you will obtain EMF equals to NBA omega sine omega t. Okay, sine omega t. This is if you're using radian mode. If you use degree mode, EMF equals to NBA omega sine theta, where theta is the angle between A and B, vector A and vector B, and omega is the angular speed. Okay, your angular speed. So omega is your angular speed. So if you use this first equation, it should be in a radian mode. Calculator should be in radian mode. If you use the second equations, it is in a degree mode. Okay, it is in a degree mode. All right, so that is because theta equals to omega t. Okay, that is what we learned before. All right, so I think that's it. Okay, let me stop the recording.